Okay, guys, I think it's time to start. It looks like we have a small group of Spartan survivors here. So let's go on. So we stopped at the part where we were going to install the Fabric CA. So we're going to follow a number of steps, 6 steps in total. We'll install the actual CA Helm chart. Then we are going to generate the Fabric CA identity, register the administrators for the order organization and the peer organization. Then we're going to enroll those same admins to actually get the crypto material that we before in the development environment got from CryptoGen. And then we'll again save the crypto material to Kubernetes, as well as generate the genesis and channel secrets, blocks and transactions, and then save them to Kubernetes as secrets, just like we did before. So, first things first, we're going to need to actually create a new namespace called CAs. So we'll just run kubectl create ns CAs. And in my case, the CAs namespace already exists, so that's fine. And I'm going to actually install the CA Helm chart. So again, I'm going to install it from the local repository. In the CA, it's going to be called CA, and it's going to be in the CA's namespace. And I'm going to set the Helm values to be those of the CA YAML. And I'll show you those values, and we'll look at the chart while this is installing. Okay. Great. So the first thing is the actual values of the CA. You can see again that the image tag is 1.3 because we're using Fabric 1.3. And in this case, we actually add an ingress here. So this ingress is enabled and has some annotations so that it knows that we're going to use the ingress controller for Nginx, and that it's going to use the Let's Encrypt production cluster issuer. So this will create real TLS certificates that will be valid in your browser as well. And this guy, if you're doing it at home, you'll want to change this to your domain name. So it might be, for example, ca.yourdomainname.com, whatever. And similarly here for the TLS, we'll have a secret for the TLS, and you'll also want to change this to your domain name as well, so that the TLS certificate will be done for this domain. We'll have persistence. So in this case, Kubernetes is going to manage again the persistent volumes, and will create a 1 GB persistent volume that will get attached to the relevant Kubernetes node and pod. We'll call our CA name CA, because we'll just have a single CA in this case, although it's perfectly possible, and we've done it to have a bunch of like a root CA and a bunch of intermediate CAs. And we enable the PostgreSQL subchart. So actually the CA chart will launch as a dependency the Postgres chart and attach to it. And an important thing is we specify the HLF tools version, which will specify that we use the config file for Fabric 1.3. And we have some certificate signing requests. So for example, it might be the country will be Ireland, the state might be Dublin, the organization might be ATEC, and the organizational unit might be blockchain, for example. You might add some affiliations if you want. The first important thing to note here that we've added relative to the development deployment is the affinity, right? So Kubernetes has a concept called affinity and anti-affinity that allows you to deploy your charts and your resources in such a way that they kind of attract or repel each other. For example, here we have a pod anti-affinity defined. That would be quite important if we released multiple CAs. If we run multiple CAs, we would want each of the CAs to be located on a different Kubernetes virtual machine or node. And this is what it will do. Basically, it will try to ensure that all these CAs will be deployed on different locations. Because we're deploying one CA, it won't matter. But the next rule of pod affinity actually does matter, because this will ask the CA deployment and pod to be located in the same machine as the PostgreSQL database, so that you'll have better connection because they'll be co-located on a machine and won't have to run through like the network. And that will allow you to co-locate both the database and the certificate authority that uses it on the same location, basically. So let's actually look at what the chart for the CA looks like. And it's here, it's the last chart that we're going to examine. So again, we have the chart.yaml with some keywords and as maintainers, the values file. So this is the default values file that is used. If you don't specify anything else in the -f command when you do Helm install, these values will be used. For example, here we don't use an ingress by default, so that's why we had to specify it. The persistence, the admin username and password, and the password will be actually auto-generated again with 24 random characters. Some database information, whether you want to, for example, use the PostgreSQL automatic dependency, or the MySQL automatic dependency, or an external database of your choice. So you can actually yourself deploy your own database separately and then just point your chart to it. But for simplicity, we just use the dependency. And here, for example, you can actually specify if you want to use an intermediate CA. So you can actually specify that you have a parent CA and then you'll become an intermediate CA. And finally, for example, here the affinities, we are not by default not defined, and that's why we define them in the overriding extra values file. And let's go to the templates. So again, we have some configuration like the Go debug level, where the Fabric CA home is, the DNS service DNS, a configuration file that gets that uses the Go templating to be customized with a lot of different things that we specify here. The config map for the database, which uses basically gets specified depending on which database type you use, whether it's Postgres or MySQL or an external database type. The deployment itself, which basically deploys the CA and waits for the initializing container to actually check that the actual dependency, the PostgreSQL chart, is ready to run. And finally, launches the Fabric CA server here, as well as gets some environmental variables from the secrets and config maps that we defined in the other files. And some liveness probes, readiness probes, some volumes that we mount, and the affinities and anti-affinities get defined here. We then have the ingress, which is what allows us to access the certificate authority from the internet, basically by allowing us to point a domain name to the Kubernetes cluster, IP address, and of our ingress controller, and then the ingress basically redirects that. The persistent volume claim that contains the actual, that sets up the actual volume that contains the data that is held by the CA. a secret for setting the CA password, which can be done automatically or by hand, and a secret for the database, so that we save the database password there, and we can retrieve it from this secret as well. And finally, a service that allows us to communicate with the CA from inside the cluster. And with that, that's all the charts. So let's get actually the CA pod. Paste without new line. So there's the CA pod. Okay, so it's listening on there. And now we should be able to generate the CA identity. The first thing that we do is we run this command kubectl exec namespace CAs and the CA pod that we defined. And we try to look for a file in var Hyperledger Fabric C/MSP sign certs cert. In this case, it's failing because it doesn't exist. So we're going to actually create it by enrolling our identity. So we're going to run the Fabric CA client, which is already installed inside our Fabric CA server, to do the enrolling, and run this command with these environmental variables that are defined inside the Fabric CA container via the Fabric CA chart. So the admin name, the password, and the service domain name server. And that will actually create the identity for the CA. Then we can get the ingress. Paste without new line. So we can see that the CA ingress. Oh, okay, I have a little. Okay, it should work fine anyway. Yeah, let's try it out. Okay, I might need to actually connect to. Okay, so for testing, I think I might have changed the CA ingress, and this is why you need to be careful with your certificate authority ingress. So I'm going to actually update it back. Let's try. Status. Let's go here. Close. We're going to actually just update this guy. HGF. There we go. Helm status. I'm just going to update the Helm chart. Helm upgrade CA stable HLF CA -f dot Helm values CA YAML. And before I do that, I will need to also get the actual Helm status CA. Okay. So we're going to actually export the admin values and run that basically. Sorry about this. And Helm values CA.yaml. So there we go. We'll just upgrade the C to actually match our ingress. Okay. So let's get the C ingress again. Paste without new line. And we're going to C URL. There we go. Okay, we see that it actually works now. We can actually, when we ping the CA and the CA info path, we actually get the certificate chain from our certificate authority. So that's all working now. Once we have done that, our CA is now working. It's a working CA, it's alive, it's happy, and it wants to get some registrations. It wants to get some identities into it. So let's give it one identity. We're going to run this command again. We're going to execute inside the CA pod our a command to register with the Fabric CA client an ID name, which will be the order administrator. So the name will be ordadmin, and with some secret, which in this case is a very, very secure password, ordadmin1 and pw. And we'll specify in the ID attributes that it's an admin. So we do that, and we've just registered an identity on our CA. Let's do the same thing for the peer admin, which basically will be practically the same command, but we need to specify a different ID name, in this case peer admin, and a different password. At least we're not putting the same password everywhere. Once we've done that, we can actually enroll our order to actually obtain the crypto material. So we're going to run this command with our local Fabric CA client. We're going to specify that the Fabric CA client home is going to be in config, so we're going to save all our MSP there. We run the Fabric CA client enroll command, point it to our CA ingress, and specify the name of the order admin and the password for the order admin, and save it in an MSP called order MSP. So that should be fine. If we run tree.config/order MSP, we should see that there is actually some MSP material. Oh, I need to actually, oops, config. I'll just delete all the old MSP material. Log my channel. There we go. Okay, good. Let's enroll again. Let's just enroll again. And we should actually get that. Yeah, there we go. And if we look at it, we'll see that we have a CA cert, a key store, and a cert under sign certs, right? We're going to create another directory in there called admin certs, because this is an admin. We'll need that admin certs directory to contain the same certificate, so that we can actually create later on the Genesis block. So we just copy the sign certs from the order to the admin certs in the order. Next, we can do the same thing for our peer, who we registered before. Again, we just run that command to enroll the peer admin. We're creating, again, a directory in peer MSP, admin certs, and we'll copy the sign cert to the admin cert directory. And again, we can do tree to actually see what it looks like. You can see that there's a cert here. It's the same cert as is here. We have a key, and we have a CA cert. All right. Now we can actually save all this crypto material to Kubernetes. So we can again get all this. Basically, this will get the organization's certificate, org cert, which is basically that. And we can create that secret. Basically, we do the same for the key, for the private key, and the certificate authority certificate. And now we have 3 secrets. So if we do kubectl -n orderers get secrets, we'll see that we created these 3 secrets in here a few seconds ago. And now that we have that, we can do exactly the same for the peer. We can create the same materials, but in the peer namespace. So again, if we run the same, but in the peer's namespace, we can get the secrets. We can see that there's 3 equivalent secrets for the peer. So that's all good. One of the things that we have here that is quite useful to know is that in the production example, we have a file called fabric CA client config. So this is the configuration that we use to access our certificate authority. And this is the chain, the certificate chain for the Let's Encrypt certificate authority. Otherwise, we would not be able to connect with the fabric CA client, because it would say that it's missing a certificate chain to actually authenticate the request to our certificate authority. So that's the important thing here. Secondly, we have also a config.tx, just like we had in the development example. In this case, again, it's also quite simple. We again have the order organization and the peer organization. Again, we only make one of the peers an anchor, but we could actually make 2 of the peers anchors if we wanted to. And importantly, in the order, we actually specify both of the order addresses that we will have, because we will have a Kafka consensus deployment with 2 orders, which is the bare minimum that you can have. Ideally, if you really are running it in production, of course, please have more. Don't have just 2. And we have also the brokers. We have the Kafka cluster location on the orders namespace of our Kubernetes cluster at the port 9092. And again, we have the profiles with the Genesis profile and the channel profile. Now that we have that, we can actually just cd to the config file again. And just as before, as we did for the development example, we can run the config.txgen profile command for the order Genesis and create an output block called Genesis block. We can again use the same config.txgen command to create a channel block. And then in the same way as we did for the development, we can just create the secrets. It's exactly the same thing. So I'm not going to dwell on it. Okay, so the next thing is the fabric order. Now this would be the difficult part where you need to install the Kafka orders, so the Kafka cluster. This would be typically quite a painful procedure involving a lot of soul searching and banging your head against the wall. Instead, we're just going to go back up one folder and use the Helm install incubator/Kafka, because this is in the incubator repository of the official Helm Charts. We'll call it Kafka HLF and put it in the namespace orders, and use the Helm values that we define in the Helm values, Kafka HLF. And I'll describe those in detail now. This is probably the longest installation that you'll see. It can take anywhere from 5 to 10 minutes, maybe 13 even. So we're going to check out for now the actual definition of the that we needed to change for the Kafka Helm chart. And then we'll take a quick look also at the Helm chart itself that is in the standard repository, so that you can have a look. The first thing to note is that you must have at least 4 Kafka replicas. This is as described in the Fabric read the docs documentation. You cannot have any less than 4 replicas if you want to have any kind of crash tolerance. We typically are using the Confluent Inc. Kafka images, and we enable RBAC in our case because we have a role-based access enabled cluster. Very importantly, here is where the pod affinity and anti-affinity rules start being quite important. In this case, we have an anti-affinity rule that matches by the label of the application Kafka. So this is the application type is Kafka, and the release is Kafka HLF. So the anti-affinity makes sure that all of these pods are going to be deployed on different virtual machines of your Kafka cluster. If for some reason you are not able to make a Kubernetes deployment, in this case that is of at least 4 machines, you may want to remove that anti-affinity rule for just this workshop, so that you'll end up with a couple of different Kafka nodes on the same machine. This is not what you should do in production, but I realize that some of you might have just free plans that limit the number of containers that you have and of machines. And the second one is a pod affinity that tries to ensure that the Kafka nodes actually are co-located where possible with a relative weight of 50 to Zookeeper nodes. The next thing that I want to put attention for is that we will need to actually override a few of the default Kafka configurations to work with Hyperledger Fabric, because otherwise it will not work or it will eventually break. The main things here is that you want to have a default replication factor of at least 3, set unclean leader election to false, ensure that the minimum in sync replicas are at least 2, and set the message size of the maximum bytes, which is related to what we have in our configuration, so that Kafka can actually process the kind of messages that are expected by the orderers. And the most important part is the log retention. You must ensure that you retain all of the logs currently forever, as the Fabric documentation clearly states that currently Fabric orders cannot handle the fact that Kafka ends up deleting some of the logs over time. So this is quite vital. Okay. In the meantime, let's actually check out how our Kafka deployment is doing. Use-ctl-n orderers get pods, for example. Okay, we're not doing too badly. We might need to wait a few minutes more for the Kafka to actually connect. In the meantime, what we're going to do is we're actually going to set up the order identities using the CA. So we're going to export this number, the number 1, so that we can just copy this command and basically register our first order instance. Before we had been registering the order administrators, now we're registering the order instance with the certificate authority. So again, with the password here, it's a very simple one, but in reality you would either specify a complex password or allow the Fabric CA to generate it for you. And we're going to enroll this very same order. If you copy-paste, you might see that you get some annoying slashes, which you need to remove here and here. And that creates the relevant materials in here. So we can again do tree, config, ord1, MSP. And you can see that all the relevant configuration materials have been created, such as the signed certs, the key store, and the CA certs. The next thing we can do is we can actually just save both of this, the certificate and the key, to Kubernetes. And that will create the secrets that we need. Since we're still waiting for Kafka, we can do basically the same thing with the second order that we have. So we just export num2 and basically register our order in exactly the same way, enroll our order in exactly the same way, we can, again, check that all the materials have been created and create the relevant secrets in Kubernetes. And now you have the actual identities in the relevant places. And the next step is just to install the actual order nodes. So I'm going to actually export back the first one and check get pods -n orders. Okay, yeah, we have our Kubernetes Kafka cluster running, so we can actually install our Helm chart. So we'll do that with our first order and with our second order. And now we basically just need to wait for our orders to come online. So we'll get the order pod and wait for it to start. But it's currently creating, so we might need to wait a little bit. For the orders, you will want to specify, again, the values file. Again, we're using Fabric 1.3. We have some persistent storage where the order will save its own data. We specify that the type of the order is Kafka instead of Solo, so that it will know that it needs to try to connect to the Kafka cluster. And 12 have its own MSP ID. Again, we specify the certificate, key, and the CA certificate that we got before, the Genesis block, and the administrator certificate. And importantly here, we again are using anti-affinity. So the anti-affinity makes sure that all of these orders are located on different machines on the Kubernetes cluster. Otherwise, having like several orders that are on the same machine doesn't give you any resilience, because if that machine goes down, both of your orders die and your network screams in pain and withers away. So now that let's actually check, and yes, our first order has started. We can check also the second one. Export, we'll get the second one. And we can get, and they've both started. Wait, it's actually the same one. Okay. So we can get the logs. Yeah, and the first one also has started. Great. So we're good to go with the Fabric peer. This is the last, basically the last part. We are going to install the CouchDB, Helm Charts, set up the peer identity, save the crypto materials to Kubernetes, install the actual peer Helm chart, create the channel, and then fetch and join the channel. So we're going to do all of these steps with the first instance. So we'll first install CouchDB again. So we run helm install stable hlf CouchDB for that particular CouchDB number in the namespace peers. And we'll do the same thing with our second one, so that we can actually have it ready for the next stage. So these guys can basically run in parallel. We can get the CouchDB pod and try to get the logs. So for now it's being created. We can actually, for example, use watch to actually check every 10 seconds what's going on with Helm status, CDB, peer 2, for example. We can check that it's creating the container for now. Again, the CouchDB instance is very similar to what we had before, but again, we have added an anti-affinity rule, so that all of the CouchDB instances are going to be deployed on different machines on Kubernetes. Okay, and CouchDB is running. And we can see from the logs that Apache CouchDB has started on the relevant localhost and port. So now we can actually set up the peer identity. So we're going to again export the first one and create and register the first peer. So again, we connect using kubectl exec to our certificate authority pod and register the relevant peer with an ID name of peer1, an ID secret of peer1 underscore password, and an ID type of peer. So that was created. And we can again enroll using our local Fabric C client with that particular peer. So I'm just going to fix that, those extra slashes that are not needed but always appear for some reason. And we have created in config peer1 MSP. We have a key store, C certs, and the sign certs. The next thing we can do is we can actually save this crypto material. So again, this basically involves saving the key here and the sign certs here to the to Kubernetes by running this. Whoa. We'll see. No, I don't want. Copy. See. Okay, there we go. So again, we get the peer sign certs and the key store, and we save them as generic secrets on Kubernetes. That's that. And now we can actually install the peer. And that will basically, we can again run a watch command here. To try and see if peer 1 is being deployed. So it's being created. In the meantime, we're just going to do exactly the same thing, but using but for the second peer, while we wait for the first peer to come online. We again register the peer. We enroll the peer. We can check that we created the relevant materials. We save all the secrets. And we install the second peer. So let's check what is going on with the first peer. So we export num1 and check the peer by getting the peer pod. So this is the peer pod. And let's get the logs for it. Yep, it started. So we're basically in business. Again, when you, if you want to look at the actual configuration of the peer, it's basically the same as you had before. The only difference is that each of them need to specify their relevant CouchDB instance and their specific crypto material and the anti-affinity to ensure that every peer ends up on a different node than the other peer. But also there is, just below, there should be an affinity to ensure that each of the peers ends up on the same instance as their actual CouchDB. Now that we have a peer running, we can run the typical commands to create the channel. So again, we connect to our peer pod, run peer channel create inside it, point to one of the orders, it can be order 1 or order 2, specify the channel that we want to join, and the channel transaction file. And we've succeeded. We can now fetch the config for the channel. So again, we do peer channel fetch config inside the peer pod for the channel block that we received, which is located in var hyperledger / mychannel.block with the channel name mychannel, and the order in this case is order 1. We receive the block, and we can join that block, join that channel using exactly that same block. We can again check that this was actually received at the correct location, and we can see that the channels that this peer has joined are my channel. And basically, we can now finally get our second peer. So we got the pod for that peer that is running on Kubernetes. We don't need to create the channel because the channel already exists, but we need to fetch the actual channel config. So peer channel fetch config with the same parameters as before. We receive the block, and we can again run the same peer channel join command inside the pod to successfully join the channel. And finally, we can run peer channel list to finally see that the peer has actually joined the channel. And now you have essentially a fully working network like this, with the CA, the orders, the Kafka, the peers joined with the my channel, and the CouchDB maintaining the world state. And basically the next section is very short. It's next steps. At ATEC we've done a few things. We contributed a chapter to the official Blockchain for Business edX course that is based on Hyperledger Composer. We also have a course on Pact and Udemy, Hyperledger for Blockchain Applications, which is a kind of introductory course on how to build applications with Hyperledger Fabric and Composer. We've released a bunch of other charts, such as the Composer and chart, and we are working on a chart for Hyperledger Explorer, and eventually we'll be soon working also on a chart for Byzantine fault-tolerant chart based on the work of Alison, who was giving a talk yesterday. And because, as you can see, there's a lot of commands to be run here, and it's quite a lot of hassle, we're also working on a deployment library to actually simplify this process so that you can provide basically a YAML configuration file and your different values files for your different components, and run a command and basically deploy the whole network end to end. And yeah. Maybe I can actually even, because we have actually time, I can actually try and do a demonstration of how that would work in principle, basically. So I can demonstrate the kind of internal deployment, if you like. And that's basically it. Yeah, Linux Foundation. And any questions until now, until we go to the next section?
What, Sasha doesn't know because I just added that. But if you want to leave us any feedback for the Helm Charts and for this session and for the workshop itself, maybe I just made a Google form, 3 questions. So it's very quick. If you want to just to give your own suggestion for us, would be appreciated.
Yeah, and what we can improve and so on.
Yeah.
Cool, nice. Yeah, questions so far, or do you guys want me to do a demo of the kind of? So
this setup has 5 virtual machines in the Kubernetes cluster.
Yeah.
You get tier 1 and tier 2.
Yeah.
So actually over the only one pod of each peer?
Yes, there is only one pod of each peer, because the resilience will come from actually having multiple peers acting in concert and actually maintaining the network. In reality, you would not just have 2 peers. You'd have at least 3, 4, 5 peers in each organization for resiliency. So you'd not just have 2 peers. And if one peer goes down, the Kubernetes cluster will actually recreate it. So for example, if one of your servers with one of your peers, one of your CouchDBs, and one of your orders goes down, it will just kind of look and say, oh, there's another server where we can actually deploy it. Let's detach the disk, reattach it to that server, put the peer there, put the order there, and put the CouchDB there. And then it will automatically heal, essentially. And because all the data will be on the disk, you won't need to kind of, there won't be typically, if you're doing on a cloud system like Azure or AWS, where you can detach and reattach these volumes, you don't need to worry about having the peer catch up, because it'll just it will need to catch up only for the last transactions that have happened. If you're doing it bare metal, then it might be a bit more difficult, and then you might need to kind of recreate the whole blockchain. But either way, it will recreate automatically these guys.
So what about auto-scaling?
So there's not auto-scaling as such, but adding extra peers should be actually quite easy. Basically, what you need to do is to create some extra material for the peers. In fact, if you want to, shall we do it? Like, we can do it now. I mean, like, I don't mind. Let's do it. Okay. I'm just going to make this stuff bigger, right? So that we can see it. Editor, general font, I guess font. Let's do it. Let's do, I don't know, 32. Okay. Yay, we can see everything. Okay, let's minimize that. So, okay, so we'll just need to basically copy this guy, right? And we'll just paste it. So we'll just create CDB peer 3, right? Nope. We don't want to add it to the thingy. And we'll just do the same thing with this one. We'll just copy and paste peer 3, right? No, we don't want to do that, but we want, we want it to point to CDB peer 3, right? Not to peer 2, because it needs to have its own CouchDB instance. And then we're going to change this so that it points to the correct secret. We haven't created those, but we're going to create them now, right? So that's all fine. We're going to have 3 peers. So let's go back to the presentation. Let's go to the Fabric peer. Okay, we're going to export num3, right? We're going to export num3. We'll deploy the Helm chart for the CouchDB. So let's check how CDB peer 3 is doing. How are you doing there? We'll register the peer, right? So we're going to just register again. And then we'll enroll the same peer. So we can do 3, peer 3. There we go, we have the material. And we'll have the node cert and the 222. So we're going to create those secrets, right? So we're just going to recreate those secrets so we can actually see that these have been created. kubectl -n peers get secrets. Yay, the CouchDB is running. Okay, that's fine. We can close that. So you can see that we have 222. Oh, what happened? Where are you? Ah, there we go. Yeah, that's the guy. Yeah, so both of them are created. They're all good. Okay, and then we can install the actual HLF peer. Paste without new line. There we go. We installed the new peer. Oops, no, I don't want. I just want another one. Yeah. So and let's check out when it's actually online. So we'll just wait for a little bit and see if we get some logs. once we have the logs, we'll have. Actually, we can actually do also this kubectl -n peers get pods, and we'll just watch. Yeah, so it's container creating. You can see it's creating. So it's just going to watch for any changes, and once it's running, it will just print a new line. Yeah, it's running. Okay, we're in business. So, okay, Nicola, I should have asked you to make like some kind of chronometration. Okay, we don't need to create a channel, but I think we're doing quite well. It's yeah, we received the block, and we joined the channel. Yeah, and we now have 3 peers in our network, and that's it. So that's even by hand, it's not that challenging now. But of course, we do have scripts to actually automate all that stuff, because it's anyway better to have something automated. For the orders, to expand the order network, that would be more difficult because you need to actually change the config.txt file and then reconfigure the network and so on to add an order. And I haven't actually yet done that. But yeah, we can keep you updated on that. And any more questions?
How are your secrets handled? Are they stored securely in an HSM? I don't know too much about Kubernetes. Maybe I'm asking.
Yeah. No. So it's a good question. Currently we are storing them on Kubernetes. Because they are encrypted on Kubernetes, they should be fairly secure for these kind of scenarios. If you want some extra security, you can probably use something like Vault, like HashiCorp Vault, or some other kind of type of secure storage. But for now, for our purposes, we found the kind of native Kubernetes secrets to be secure enough, especially if you use roles-based access in a good way. So that's, I would say that, yeah.
How would you handle deployment over different sites?
So over different sites, that's a really good question, and this is actually why we created the ingresses. So you saw that we used an ingress. So for example, we can actually, so here let's do ca.hgf.8techtest.info, I think. Let me see the actual domain. XYZ. Oh, very nice, very good. XYZ/CA info. So you can actually, yeah, you can access it from. Why is it making it all too small? Yeah, there we go. So in the same way that you actually have an ingress that links a request from outside the Kubernetes cluster to the service of the CA and then to the pod of the CA, you can do exactly the same thing with the orders and the peers. I haven't demonstrated it here, but we actually have like a test deployment somewhere here in my other repository. Okay, some projects. Basically, so I'm going to open that and show you some, like for example, the ingress version. So here, for example, we have the values for the order. So for example, this is like a basic deployment. So we just essentially add an ingress. We need to actually specify this backend protocol bit for gRPCs because we're doing secure gRPC. And we need to enable TLS, basically, for the order, for it to actually work correctly. In this case, we're using 1.2, but we can use 1.3, it doesn't matter. And then we just need to specify some extra secrets for the order related to the TLS. It's a little bit more painful to do, especially if you do it by hand, but we're actually automating that a bit now, like in the deployer. And but yeah, so that's how it would work. And basically, you'd have exactly the same thing for the peer. So you'd have the, again, this extra configuration for gRPCs. You'd have your host where you want to save it. For example, here it's atech test, but hlfdev. And then we'd have, again, the TLS specified here, and some TLS secrets here. And once you have those, basically the peer and the order can talk to each other using basically TLS. And yeah, that's essentially it. And then it doesn't matter where your actual peers are located, because you can have for example, the Cello guys, they when they are trying the Kubernetes stuff, they are doing a kind of federated cluster where you have different organizations, different namespaces, which is completely fine if you trust the person who has the Kubernetes cluster. If you don't, then you can actually have different Kubernetes clusters, one for one organization, one for the other organization, one for another organization, one for the orders, and then they just communicate with each other through these ingresses. And in that case, you don't even need all of the guys to have Kubernetes clusters. You could have a Kubernetes cluster for organization 1, and then organization 2 might be wanting to run bare metal. The other organization might want to use native AWS, VMs, and so on. So it should work more or less out of the box. Yeah.
Suppose you would connect different sites together by creating a virtual private network. In the event that you don't want it to be accessible from the internet.
Yeah. This would be, this definitely would be one option. One of the other thing, I mean, even if it's accessible through the internet, that is partly where the TLS, mutual TLS, makes it considerably more secure, because they basically the actual peers will know what the certificate authorities they can trust, so they'll have a set of trusted certificate authorities, and if they receive requests from someone with a public key that is not trusted, they'll be like, oh my god, yeah, I'm not listening to you. Of course, it's probably easier to have a private network, but actually the TLS should enable you to even actually have them available on the open, essentially.
Yeah, if you would send a lot of requests to a server to capacitate it.
Yeah, denial of service. Yeah, you could do that definitely. Yeah, so a private network would be a better option if you're afraid of the denial of service. Definitely, yeah. Yeah. Any more questions? Okay, so we have still 27 minutes. If you want, I can try and then see if I can make a demo of like making like a basic deployment. So basically, let's just create a new basic deployment. For example, these guys. Yeah. Okay. Fine. Let's. Just copy this one. Copy. New. Okay, we're just going to paste. So I'm just going to do an HDF demo deployment. And the HDF demo deployment I'll need to delete a few of these folders with existing stuff. Delete. And of course, please bear in mind that it's actually a work in progress. So if it doesn't work, don't kill me. It's still in progress, and I'm just going to use my current AKS cluster. So let's try it out. And in this case, we're just going to deploy it to the blockchain. I'm actually just going to delete all the stuff. So I'm going to actually delete all the stuff that we have created so far. Peer 3, Peer 2, Peer 1. In fact, I think actually I think I actually saved some information on how to delete everything here. Yes, there we go. So I'm going to actually delete all of our guys that we created. Okay, where is my? There. So we're going to just delete and purge all of our previous components, such as Kafka, and also Helm delete purge CDB peer 3 and peer 3. We'll delete the stateful sets, which don't exist anymore. We'll delete all of these persistent volume claims. Delete all these secrets. And all the peer stuff. Okay. Also peer 3, just in case. The cert. Okay. And we'll delete all the crypto material, which is fine. Okay. So next thing that I'll need to do is I can close that because I don't need it. We'll deploy it all here. We'll have 3 orders and 3 peers. And so that's going to be the HDF demo. Okay. I think let's try it out. It's cd dot deployer. Okay. HLF setup c.py, and we're going to do test deployments. We're going to go hgf demo, HLF config, and we're going to run. Whoops, and I need to actually run it with -f. We'll put it on verbose so that it complains. So it's going to install actually 3 certificate authorities. We're going to run one certificate authority that's going to be the root, and then from this root certificate authority, we're going to deploy 2 certificate authorities, each of which is going to be a. Oh my God! I've actually messed one thing up. I need to actually edit the values. One of the certificate authorities will be. So I need to actually change the ingresses here. The root certificate authority will not have any HGF will not have any ingress, so it will be only internal. But the order and peer certificate authority will actually do have, and the same with. Actually, we're not. Sorry. Oh, yes, that's right. Okay, let's go R. Okay, Control-Shift-R in that directory, and to end. It's going to get replaced with HGF. Replace all, place, and then Control-Shift-R. Oops, 8tech test.xyz. Place all, place, and I think that should be fine. That should be now fine. Okay, let's try it again. Yeah, there we go. And so yeah, and then there will be one certificate authority that will be intermediate for the peers and one for the orders. And interesting. Test deployments. Okay. Delete, purge, RC, PG. And of course we need to replace this guy, HDF demo. There we go. kubectl-n blockchain get PVC. There we go. So, okay. Okay, it's been a long day. Okay, that looked more successful. So, thank you. Yeah. I'm going to be cheeky. I'm going to go to the loo and be right back. So, just. Yeah. So this is So yeah, we can stop it here. We can. I'm going to just leave this on so you can see how it actually auto deploys if you want. If it's boring, you can just leave. It's fine. And please do get in touch with us if you have any questions or you want to contribute. I'll just leave briefly for the people who want to get in touch with us. I'll leave our email addresses so you can. Oh, well, you actually have them in the presentation. So, and yeah. And I'll just leave this on running. And